بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Today we're going to continue talking about numerical sequences, and specifically we will talk about the convergency of a numerical sequence. Well, let's continue. Definition 2. A sequence UN is said to be convergent if and only if its limit exists. And a sequence that is not convergent is called a divergent sequence. So we have two kinds of sequences. We have the convergent sequence and the divergent sequence. The convergent sequence is a sequence whose limit exists, means that its limit is a unique real number, and a sequence that is not convergent is said to be divergent. UN is a sequence. We need to study the convergency of UN. Convergency here doesn't mean that it's convergent. It means it could be convergent or divergent. Let's see the first sequence. So remember, to study the convergency, we have to see whether the limit exists or not. We find the limit of the sequence UN. This is the limit of this quantity. We get positive infinity over positive infinity. If we use the leading term or L'Hopital's rule, we get negative 1 over 3. The limit exists means that the sequence is convergent. Well, this sequence, we find its limit. Remember, 2 is greater than 1. So the limit of this quantity specifically is positive infinity multiplied by a minus becomes negative infinity over negative 1, which is positive infinity does not exist, so the sequence is divergent. Well, this one, we also find the limit. Here, remember, negative 3, we have to divide the question into two parts. If n is even, we're going to get positive infinity. If n is odd, we get negative infinity. So the limit does not exist, and the sequence is divergent. Well, let's apply together. UN and Vn are two sequences defined as follows. First, we need to find U1, U2, and V0, and we need to deduce that the sequence UN is neither arithmetic nor geometric. Try to do it alone. Let's see the answer. Well, U1 is minus 1 over 3 U0 plus 4. We just substitute, we get 8 over 3. U2 is minus 1 over 3 U1 plus 4. We also substitute, we get 28 over 9. And V0, we substitute it here. V0 is U0 minus 3. And we do know U0, which is 4. So V0 is 1. Now, to tell whether U1 is arithmetic or not, we have to see U2 minus U1 is 4 over 9. It doesn't equal U1 minus U0, which is negative 4 over 3. So we can say that the sequence is not arithmetic. And U2 over U1 is 7/6, which is not 2/3. So we can say that the sequence UN is not geometric. Remember again, if we need to prove that it's not arithmetic and or it's not geometric, it's enough to give specific examples like this. Whereas if we want to prove that UN is an arithmetic sequence and or is a geometric sequence, we need to take it in general and we need to study it in terms of n. Let's continue. 2a, show that the sequence Vn is a geometric sequence. Try also to do it alone. Okay, to be a geometric sequence means that Vn plus 1 should be Vn multiplied by a constant, while Vn plus 1 from here is Un plus 1 minus 3, and we know that Un plus 1 is minus 1 over 3 Un plus 4. If we just substitute, don't forget to put negative 3. This is going to be this quantity, and finally it will be minus 1 over 3 Vn. So we can say that Vn is a geometric sequence with common ratio R, which is negative 1 over 3. Right, in terms of n, Vn and Un, it means we need the general terms of Vn and Un. Try to do it alone. Let's see. Applying the formula of the general term of a geometric sequence, we can say that Vn is V0 multiplied by r to the power n, and this is r to the power n, and we know from before that V0 is 1. Well, how do we find Un? If we know Vn, we can tell what is Un from here. Remember here, Un is not an arithmetic sequence and it's not a geometric sequence, so we don't have a general formula for its general term. That's why we have to see the relation between Vn and Un in order to find the general term Un. So Un here is Vn plus 3, and we know Vn is negative 1 over 3 to the power n plus 3. Let's continue. Well, to see, we need to study the convergency of Un. Try to do it alone. Okay, to study the convergency, we need to find the limit, and the limit of this quantity is 3 exists, meaning that the sequence Un is a convergent sequence. Part 4, Sn is V0 plus V1 plus V2 plus blah 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 plus Vn. So it's the sum of a geometric sequence. We need to show that the sequence Sn is convergent. Try to do it alone. Let's check. Applying the formula, Sn is V0 into 1 minus r to the power n plus 1 over 1 minus r, which is going to be, after simplification, equal to this quantity. Now, to prove that Sn is convergent means we have to find its limit, and the limit should exist. The limit of Sn is the limit of this quantity, and remember that negative 1 over 3 is between negative 1 and 1, so its limit is 0. So this quantity, this specific quantity, tends to 0, and the limit would be 1 over 4 over 3, which is 3 over 4, which is a unique real number that exists. Then Sn is convergent. Now we're going to talk about sequences and inequalities. If Un and Vn have limits and Un is less than or equal to Vn for every n, then we can say that the limit of Un is less than or equal to the limit of Vn. And this works for the 4 inequalities. I mean, if Un is less than Vn, we can also apply a limit here and there, and if Un is greater than Vn, we can apply the limit. Well, specifically, if the limit of Un is plus infinity, the limit of this quantity is plus infinity, and Vn is greater than Un, means that the limit of Vn is greater than plus infinity, and something greater than plus infinity is plus infinity. And if the limit of Vn is negative infinity, well, the limit of Vn is negative infinity, and the limit of Un is less than negative infinity, and less than negative infinity is going to be negative infinity. These two properties are called the neighborhood properties. So, in general, greater than plus infinity is plus infinity, and smaller than negative infinity is negative infinity. Now, if Un, Vn, and Wn are 3 sequences that have limits, and Un is smaller than or equal to Vn, smaller than or equal to Wn for every n, we can say that the limit of Un less than or equal to the limit of Vn less than or equal to the limit of Wn. And specifically, if the limit of Un is equal to the limit of Wn, remember, the limit of Un is equal to the limit of Wn, then we can say that the limit of Vn is equal to both limits, and this is what we call the sandwich theorem. Well, if I come and say that I have a certain quantity which is sandwiched between 1 and 1, it's greater than or equal to 1 and smaller than or equal to 1, in this case it would be nothing but 1. Let's see this example. Un is a given sequence defined as follows. The question is to find the limit of Un. Well, I can say that un is between half to the power n and 2/3 to the power n. If I apply a limit here, there, and there to each part, and we calculate this limit, you can see that the limit of the the sequence is 0, and the limit of the last sequence is 0, and un is sandwiched between 0 and 0. So we can say that the limit of un is 0. Let's take this application. We know that un is greater than this quantity, and the question is to find the limit of un. Try to do it alone, and let's see the answer. Well, un is greater than 3 over 2 to the power n. If we apply limits here, remember in the case of limits of sequences, we always let n tend to plus infinity. So the limit of un is greater than the limit of this quantity, but this quantity is plus infinity because 3 over 2 is greater than 1, and the limit is greater than plus infinity means that it should be equal to plus infinity. This is by the neighborhood property. Well, application 5, un and vn are two sequences. We need to answer by true or false. If un is smaller than vn and the limit of un is minus infinity, can we say that the limit of vn is minus infinity? Try to think about it. Well, this is false because if the limit of un is negative infinity and vn is greater than negative infinity, it could be any real number and it could be plus infinity, so we have different answers. If un is less than or equal vn less than or equal to wn, and the limit of un is equal to the limit of wn is equal to plus infinity, then the limit of vn is plus infinity. Try to do it alone. Well, this is true. In this case specifically, we can say if the limit of un is plus infinity and vn is greater than plus infinity, so it is plus infinity. Now, if un is greater than vn and the limit of vn as n tends to plus infinity is negative infinity, then the limit of un is negative infinity. Try also to do it alone. Well, this is also false because something greater than negative infinity could be any real number or positive infinity. Now, Rami or Rima, we need to calculate the limit of this quantity as n tends to plus infinity. Let's see. Rami said if we take 2n in common, we get 1 minus 3 to the power n over 2 to the power n, which is 1 minus 3 over 2 to the power n. Well, the limit of 2 to the power n is plus infinity, and the limit of this factor is negative infinity, and the final answer is negative infinity. Let's see Mira. Mira said if we take 3 to the power n as a common factor, we get here 2 over 3 to the power n minus 1, which is plus infinity multiplied by minus 1, because the limit of this quantity is 0, and this is equal to minus infinity. Well, which one do you prefer, and which one is correct? I think both are correct. I prefer Mira's method in this case because the limit of 2 over 3 to the power n tends to 0, and it's easier to deal with zeros. Here the limit is infinity, and we might get some problems with infinities, whereas here the limit is 0. Well, again, both methods are correct, but I prefer Mira's method. Thank you.